All right, and ladies and gentlemen, welcome once again to the Simkins Physics Corner. Google is down, so I can't upload anything right now, but I'm making videos anyway. Let's remember this time when 2020 just kept getting better. Here we have a little bit of conservation of momentum this morning. And so let's take a look at what we did last week with a quick little easy example here. So here's a little skateboard person. You're going to be running like this. It says your penny board, is just a tiny little skateboard, is sitting on the ground at rest. I know my art skills are amazing. I can't help myself. It says, we got a penny board, and the strategy we went over last week is this idea of the PMV stacks. All right, P meaning momentum, M for mass, of course, and V for velocity. So it says the penny board has a mass of 10 kilograms, and you jump on with a velocity of 4 meters per second. Now, it also said that the penny board was at rest, and so do we know, let's see, what is the combined velocity of you and a skateboard? Your mass is 80. That's what I was looking for. 80 kilograms. I should probably have just read the whole problem. Probably would have been a lot easier. I always do that. But as we organize our information here, we come to see that one thing is moving and has mass, and if you have mass and you're moving, mass in motion means you have momentum. Holy alliteration, Batman. And so if I do this for P, I can find that my momentum running into there was 80 times 4, which I really don't need a calculator for because it's 320, but it's early, so we want to make sure we're getting things done correctly here. So 320 kilogram meters per second. Now, a board at rest, if I did m times v, if I did 10 times 0, I would get 0 kilogram meters per second. And so the big idea from last week is that the total momentum, that's sigma sign, means total momentum before a collision, the I meaning initial, is 320 kilogram meters per second. And the rule is that the total momentum before a collision must be equal to the total momentum after a collision. That's always true. It doesn't matter what kind of collision you have. We'll talk about those today. But momentum is always conserved in our system here. So let's see how that would work out. Well, that means our total still has to be 320 kilogram meters per second of momentum. But now what we have is we got the little guy here on the skateboard, and they are moving together as one mass. And so one of my pro tips for collision problems, and particularly those where things stick together, like we'll see one where two bumpers of cars stick together, you can just consider that one large glob of moving stuff. What do you mean? Well, we had 80 and 10 kilograms separately, and so if we combine them together, we'll have 90 kilograms. Not rocket science. Now, here's the big idea. Don't miss this step right here. The first thing we said was that the total momentum has to stay the same. The second thing we say is that where does that momentum go? Now, in this case, it's very easy to figure that out because there's only one object that can hold that momentum, if you will, or have that momentum. And that's the skateboard plus person object. They stuck together. And by P equals mv, our velocity here would be P over m, which would be 320 over 90. So let's go ahead and drop that guy in there. 3.55 meters per second. All right, now let's see what happened here. Well, that speed is slower than our initial speed. Why is that the case? Well, if you're running and you jump and now you stick to something, that other something has to get moving. It has to hold some of the momentum or gain some of the momentum that you originally brought to the system. And so if we increase the mass of a system, let's look at it as P equals mv. If we increase the mass, you skateboard, right? We increase the mass. If you increase the mass but the momentum stayed the same, the velocity has to drop. And that's what you see right here. It dropped from 4 to 3.55. So the two big ideas from last week were this idea that the total momentum before is equal to the total momentum after a collision, and our strategy of using PMV stacks to identify where the momentum is or what object has that momentum. Now, big idea for today are the two types of collisions. You see, we will see these terms all the time, and this is a lot of words. So let me break it down for you. An inelastic collision is one where energy is not conserved. And an elastic collision is one where energy is conserved. All right? So that is all you need to know. Elastic collision is when energy is conserved, and an inelastic collision is when kinetic energy is not conserved. All right? So one more time. Elastic means that energy is conserved, and inelastic means it's not conserved. The energy is not conserved. Now, the momentum is always conserved, right? But the kinetic energy is conserved only in an elastic collision. Now, you'll see this other term, perfectly inelastic collision, and it's got a kind of a funky definition, all right? It says they stick together, so that's the one thing you want to take from it. If you see a perfectly inelastic collision, you say, okay, they definitely stuck together. And there's this term, maximum kinetic energy loss. That's kind of amoebus and hard to define. So when you see perfectly inelastic, you want to think the two things stuck together. When you see inelastic, you know that the kinetic energy is not conserved. And when you see elastic, you know that the energy is conserved. So let's take a look at how that might play out in a situation here. So we have two cars here. There's a car of this much, car of this much mass, and it stopped. That's me after getting a free Baja Blast from Taco Bell. Waiting for a free break in traffic before merging with cars on the highway. A pickup of mass this comes up from behind it with a velocity of 17.5 meters per second and hits the stopped car. What an idiot. Assuming the collision is elastic, energy, kinetic energy specifically, is conserved. How fast is the pickup traveling just after the collision if the car is pushed straight ahead onto the highway at 20 meters per second just after the collision? So let's drop some numbers on our diagram here. All right. Basically, the mass here is going to be 1.5 times 10 to the 3 kilograms. This guy is 2 times 10 to the 3 kilograms. This guy was going 20 meters per second, and then he bumps this car. Sorry, this one was not going 20. This one was going 17.5. We'll call that the V initial of that car. And we don't know the V final for that car, but we do know the V final for the tiny little guy. So really, I should have set up this diagram a little bit differently. But let's look at the before the let's look at the before the collision and after the collision. So before the collision, wow, great job, Simkins. Before the collision, the little car is at rest. So if I do the PMV stack for the tiny car, well, actually, let's keep it consistent with our picture over here. I'll call the tiny car the second mass. So this guy has 1.5 times 10 to the 3 kilograms of mass, but it's not moving, so it has no momentum. So that's the red car before the collision. Before the collision, though, the truck has certainly a lot of momentum, 2 times 10 to the 3 mass and 17.5 meters per second for velocity. We're going to multiply those two numbers together. So 2e3 times 17.5, that's going to get us quite a bit of momentum before it, 35,000 kilogram meters per second to be exact. Now, that's before the collision, and so if the truck has 35,000 kilogram meters per second momentum and the car has 0, you add them together, the total momentum before the collision is 35,000. And if the total momentum before a collision is 35,000, then the total momentum after the collision has to be 35,000 because momentum is always conserved. Now, energy is not necessarily always conserved. In this case, though, is it? Well, let's see. It was in here somewhere. Here we go. Assuming the collision is elastic. And so we're going to check after we're done the momentum part to see if the energy indeed was conserved. And then we know it's elastic. So let's go ahead and break it down for the truck here. The truck, PMV, is going to be a little bit tricky. Oh, man, not this again. Hold on a sec. Get this, keep them. Yep. When I start writing too many things on PowerPoint, it starts getting weird on me here. All right, so here we go. The mass of the truck is 2 times 10 to the 3. We don't know its final velocity. Oh, we don't know anything really about the truck. All right, let's go to the car. The car, PMV stack. Well, we do know that the car is moving 20 meters per second after the collision. We also have been told that its mass is 1.5 times 10 to the 3 kilograms. And so if I calculate the momentum of the car, actually very similar, nah, not really, 1.5 e to the 3 times 20. All right, now the car has 30,000 kilogram meters per second of momentum. Now, let's put this all together here. If the car has 30,000, but my system total has to be 35,000, then the truck must have 5,000. All right, because these two P's up here, the momentum of the truck plus the momentum of the car, these two numbers right here have to add up to the total because the total momentum stays the same for our system no matter what's going on. And so we have P equals MV. We plug those in. We got 5,000 equals 2 times 10 to the 3 times V. Divide both sides by 2 times 10 to the 3. So 5,000 divided by 2E3. And that's going to get you 2.5 meters per second. So let's take a step back for a second. You may be like, Mr. Simkins, the truck came in at 20 meters per second. How is it that the car was moving at 20 meters per second? The same, sorry, not even that. The truck came in with 17.5 meters per second. How is it the car moved faster? Doesn't that like violate momentum or something? No, because the car is smaller than the truck. Oh, okay. All right, I'm starting to get somewhere. And think of it this way. What would physically happen? A big truck would come in. It would hit the car, so the car would jolt forward pretty significantly, but the truck doesn't even necessarily stop. And in this case, we verified that it doesn't. It doesn't stop. It has 2.5 meters per second of velocity left over. All right, but what is true is that the momentum is conserved for our system. So let's do an energy check. What is the KE before? The KE total, I should say. And what is the total KE after? Well, this is just a matter of plugging in 1/2 mv squared for all of our objects. All right. So obviously the car at the beginning would have 0 kinetic energy, but we would do 1/2, m 2 times 10 to the 3 and 17.5 meters per second squared. And we want to check to see if that is equal to what we have on the other side. So 1/2 2 times 10 to the 3, 2.5 meters per second squared. Not meters per second squared, but you got the idea. Look at the equation. That's the truck's kinetic energy after. And then we also have the car's kinetic energy after. So it looks a little something like this. And it turns out that when you plug all those numbers in to check, is the kinetic energy before the collision equal to the total kinetic energy after the collision? The answer is yes. All right, so here's the work for that. Here's the numbers that work out. It is an elastic collision because the total kinetic energy, the total kinetic energy before the collision is indeed equal to the total kinetic energy after the collision. Sweet. There was another problem. Here we go. This one. Let me clean this up for you here real quick. I'm going to keep the other annotations. But yeah, you know what? This isn't that complicated, so let me just show it to you. All right, I'll just show you the completed version here. This second scenario, I'll put my face right in the diagram here. It says, instead of colliding elastically, suppose the two vehicles lock bumpers. All right, lock bumpers, remember, stick together, that's perfectly inelastic. Sometimes they use that terminology. And inelastic means the energy is not conserved. And so it says, with the same initial conditions, find the speed at which the car would be pushed onto the highway. So I'll move myself out of here. So we see in this first diagram down here, we got moving truck, stationary car. We found the total kinetic energy. So the total kinetic energy here was 306,250. For the after scenario, though, the after scenario is where things get interesting. All right, using this idea of the total momentum before the collision was 35,000. The total momentum after the collision is 35,000. And we would use the combined mass of those two cars when they stick together. But the process of sticking together is a process called deformation, or to deform, right? If the bumper hits the other bumper and they stick together, there's a lot of energy going on to do work on the bumper or the crumple zones of the cars, whatever you want to call it. And so there is going to be energy loss. By using the conservation of momentum for these two things that stick together, we find that the combined velocity of the car plus the truck stuck together is 10. All right. And when we take that total mass of the car plus truck and the total velocity of the car plus truck, and we plug it into the kinetic energy equation, look what happens. We started with 306,250 joules of kinetic energy, and now we're down to 175,000 joules of kinetic energy. Kind of confusing at first, pretty magical, but this is what always happens. When things stick together, it's impossible for the energy to be conserved. All right, and that's why if you think back to that roller coaster problem I gave you, I have to go rewrite it. Either that or now we can go revisit it knowing what we know, because the two blocks stuck together at one point, you can't conserve energy if that's the case. All right, so if you just try to use the straight energy approach, it's not going to work. You have to throw your momentum knowledge in there as well. Okay, so to recap for today, when we continue on with our lesson here, if Google ever comes back up, I have a video showing the solution for a two-dimensional collision. Because, ladies and gentlemen, momentum's not just conserved in one direction. Oh, no. It's conserved in all directions. Okay? And so the problem we're going to look at together is, what if this little puck comes in here and glances? You see how it's not hitting the middle of this guy, but it's hitting this kind of the side, and it goes pew, and kind of shoots off. Well, the momentum in the horizontal direction before the collision has to be equal to the momentum components horizontally after the collision. And while neither of these are moving up nor down, right, the total vertical momentum before the collision is 0. That means that the vertical momentum of this guy plus the vertical momentum of this guy, see how they're opposite directions, has to also add up to 0. So that's our next topic. Tune in next time for the Two Pucks Collisions Simkins Physics Corner episode. Until next time, Mr. Simkins in the Simkins Physics Corner.